Barry Cooper, Mr. Herman Lam, distinguished fellows and council members of the Hong Kong Computer Society, ladies and gentlemen, may I, on behalf of the Society and Cyberport, welcome you to this distinguished lecture series lunch to be given by Professor Barry Cooper. Now, let me tell you why you are here, and I have to thank a few persons. We were reminded by Mr. Cambridge Wong, Y.B. Yeung, and Dr. C.K. Wong early on in the year, or in fact late last year, that 2012 is the centenary year for Alan Turing, who is well known as the father of computer science. And as a Hong Kong Computer Society, in terms of professional development, community awareness of ICT, we are now involved in organizing a number of activities for the Alan Turing Centenary year. We are very happy that Professor Barry Cooper is here. Professor Barry Cooper is the head of the Alan Turing Centenary Year Advisory Committee chair. So he's a global coordinator, and Hong Kong CS sponsors his presence in Hong Kong, and he's involved in a number of activities this couple of days. Let me just talk briefly about Professor Barry Cooper. He was born in 1943. Sorry to reveal your age. Is a British mathematician and compatibility theorist, currently professor of mathematical logic at the University of Leeds. His book, Computability Theory, has made this basic but technical research areas accessible to a new generation of students. He's a leading mover of the return to the basic questions of the kind considered by Alan Turing and of interdisciplinary development related to computability. Professor Barry Cooper graduated from Oxford University and got his PhD from University of Leicester. He's currently president of the Association of Computability in Europe and is chair, as I said, of the Turing Centenary Advisory Committee. Now, yesterday, Professor Barry Cooper gave an intellectually challenging speech to a cross-section on Alan Turing, on a cross-section of the public. But it was a 1 hour and 45 minutes lecture. Now today, it is a lunch, more informal, more relaxed. It's going to be half an hour, followed by about 10 minutes of Q&A. So I have asked Professor Cooper to talk more on the life and legacy of Alan Turing. Maybe some anecdotes regarding his life, as well as, for example, his work on Enigma, which is a crypto machine, breaking the code of the crypto machine by the Nazi Germany, and thus shortening the war by Second World War by a large margin. Half jokingly, I challenged him yesterday. I said, if you can give a half an hour speech without a single mathematical symbol, it would be really, really, intellectually and both challenging, less challenging for us. So, therefore, on your behalf, may I present Professor Barry Cooper. Thank you.
Well, I'm very happy to be here in Hong Kong. Thank you very much for inviting me, and thank you to Cambridge for all he's done for my to smooth the way for my visit. I understand that a lot of people here are very important people in the IT industry, and it's not my usual audience. And I have tried to observe the requirement of no mathematical symbols, but there may be X names sneaking at some point. If you look at the title page here, you'll notice some of the kind of ingredients that I'm going to allude to. I'm going to obviously the apple has become iconic in the case of Turing, and the relationship to modern computing through for instance, through this old logo of Apple Macintosh. And there's an Enigma machine, which in a sense is what was quite an important ingredient in the development of the computer through decrypting and so on during the Second World War. Now, I can't promise that I'm not going to talk about challenging ideas, but I'll try not to make them too challenging. I'm going to briefly review Turing's career. Of course, in the early days, he was at boarding school, and his parents were in India, and the two boys, Alan and his brother John, were kind of farmed out to foster care, and then later on to boarding school and so on. And Alan, of course, was a very what makes him kind of attractive to a lot of us is that we all care about ideas and technology and the way computation works in detailed ways. Alan was very much into this from an early age, and you can see that he's thinking something there. And you look at the people around him, that gives you an idea of the society that he grew up in. It's a very much different world to what we have now. Anyway, Sherborne School, interesting place, and Cambridge knows something about this. Now, one is used to thinking in terms of our heroes being perfect people and having all these wonderful attributes, and well, no, actually, they're often very much they're complex people. Here's his report from when he was nearly 15. And you read this and you see that actually he wasn't the perfect pupil. In fact, he was an eccentric person, and it's kind of amusing in a sense. I mean, those of us who've had to suffer school and brought reports home to our parents that weren't always what we'd like them to see, we see that, for instance, mathematics, a very good term's work, but his style is dreadful and his paper is always dirty. And I think things got better. This is kind of early on in his school career. Things did get better as he went on, and that you will find remarks that say that this guy is unusual and he's a genius and he's going to be something one day. But it wasn't. The route to achievement wasn't a smooth one. And this is towards the end of his life. Of course, he ended his days in Manchester, and I think in some ways some of his most important work was done in Manchester. Apart from the universal Turing machine, which we'll look at in a minute, some of the biology and the artificial intelligence and so on, and some of the programming work were associated with Manchester. And this house here that you see is actually the house that he lived in the years before he died in Manchester. And you can go and see this house. It's now got a plaque on it to tell you that it's his house. And these are the people that actually live in the house now. It's not a museum or anything. It's got ordinary people living in it. But they're nice people. If you do go to Cambridge, to Manchester, you can go and knock on their door and say, "Look, I've come all the way from Hong Kong or wherever," and they'll let you see something. The statue. This is probably one of the nicest statues of Turing. It's a picture of him with his apple there, sitting on a seat in Sackville Square in Sackville Place in Manchester. Okay, what did he do? What makes him important in the history of the computer is his model of what it means to compute. And of course, computation has been important to humanity right from early times, and we've always wanted rules for doing things. Rules enable us to repeat tasks and to execute them according to ways in which we've learned to do them, and we have the notion of algorithm, which goes back to the earliest times. But the idea of if I wanted to actually get a machine to do this, one built something that had levers and cogs and was designed to do a particular task. So we had calculating machines from like the Middle Ages onwards, and we had clocks, for instance. I mean, that's a calculating machine in a sense. But every time you wanted a computational task done, you built another bit of hardware. Now, what happened in 1936 was that Turing came up with a very kind of abstract idea of what would carry out a computation, and it was kind of broken down to its simplest elements, and it's called a Turing machine. Now, I'm not actually giving you a definition of a Turing machine, but here's an embodiment of a Turing machine. This graphic here is by an artist in Houston, Texas, and she's given us a Turing machine, but embodied in a sense as Turing himself. And you see that the essential ingredients are a tape for recording data and mechanisms for changing the data on the tape, and Turing himself is the mechanism in this case. He's got a pencil and he's using binary notation, and he's going to change zeros to ones and ones to zeros and so on. And of course, what's not the important thing isn't actually in the picture. It's the program. And he had this idea that the actual hardware was simple, and the program was what did all the work. And this gave rise to the idea of the universal Turing machine. This is essentially the idea behind the stored program computer that we have now. So nowadays, when you want to do a computation, you don't throw your laptop away and buy another one, at least not every day. And what you do is you pick up a piece of programming and you put it into your machine, and you've got a universal machine. It understands the data that you put in as giving you a program, and you're able to do some complicated tasks which wouldn't have been done in the past. So you had the universal Turing machine giving birth to the idea of the present-day stored program computer, and that's due to Turing from 1936. Now, there was one thing, the whole point. This was a paper in pure mathematics, and the point of this paper was actually to show that computers couldn't do everything. So at the same time he came up with the idea of modelling computation and the idea of the universal Turing machine, he also solved a very important problem in pure mathematics, which was set by David Hilbert, famous pure mathematician of that time, of earlier days actually. And in doing this, he discovered incomputability, which is the limitations of what a computer can do. And I guess in the IT industry, you're daily presented with barriers to what you can do now, and you're trying to extend the limitations and go to new dimensions and find out new things that computers can do. And this is in a sense is what Turing was thinking about. He discovered the limitations of the Turing machine, and that opened the door to thinking about computation in a wider context, and we'll see a little bit about that in a minute. History of the computer. You come up with a Turing machine. It's very simple, a simple abstract model, but actually embodying that in the real world is still a lot of work to do. And actually getting machines that carried out that idea is very complicated. A lot of very ingenious thought went into that. Ways of actually storing the data. You didn't want a tape with somebody with a pencil. You wanted something electronic that did things quickly and reliably. Here's Conrad Zuse, who was essentially an engineer and contributed to the early computers in ways which were quite independent of Turing's mathematics. And a lot of people that worked on computers at that time didn't know a lot about universal Turing machines. John Atanasoff, first recognised legally as the first electronic computer. The people who really pushed things forward in Philadelphia, Eckert and Morshley. Now the stored program idea was not really embodied until about 1948, and of course the Manchester Baby, which was a very kind of elementary prototype, that goes back to Manchester 1948. Maurice Wilkes in Cambridge, he got a rather more useful version of the stored program computer. Actually was used by the university to do various tasks. And then of course the Eckert and Morshley's machine, which in a sense took things to a new level and set the seeds of the domination of the American computer industry in later years. A lot of the earlier ones, like Charles Babbage, I don't know, do many people know about Charles Babbage? Okay. he was back in the 19th century, and he was working with real mechanics. It wasn't the electronic computer, but it was programmable, but it wasn't a stored programming computer. So a lot of these early machines, like Colossus, for instance, at Bletchley Park, and Zeus's machines, they weren't true computers in the sense they weren't stored program computers. Bletchley Park, of course, is what in latter days has made Turing famous. For many years, what happened at Bletchley Park was completely secret and was kept secret by the UK government with the power of the Official Secrets Act. And there were 10,000 people worked at Bletchley Park, and they went home and they weren't even able to tell their families what they'd been doing. And it wasn't until the 1970s that these machines that you see here became more common knowledge. Actually, the bomb that you see here, this was one of Turing's machines. It isn't actually an original. They were destroyed. This is a rebuild, and there are kind of enthusiastic computer enthusiasts that volunteers at Bletchley Park, and they put in hours and hours of work rebuilding these old machines from plans and photographs and so on. If anybody, those who've been to Bletchley Park will know this is very interesting. You can see it working, and you can talk to people who know the details of how they work. Turing was involved in building early computers. This is the ACE that he was involved in building back in the 1940s. He eventually hit the usual problem that one of funding, which he had frustrations in getting his machine built, and he went off to Manchester before it was completed. It was now his role in the early computer and at Bletchley Park has been honoured in various ways. There's the Turing problem on postage stamp, which came out this year, and this was a nationally used postage stamp, and you can buy first day covers produced by Bletchley Park Post Office with this stamp on it. This is a nice slate statue of Turing also at Bletchley Park. So when Turing went to Manchester, nobody knew the tremendous work he'd done at Bletchley Park, and so I think people there building computers probably thought Turing, with his eccentricities and weird ideas, was a bit of a nuisance, and so he did some programming for the early Ferranti machine, and there you see him essentially an observer of the history that was being made at that time. He knew Dietrich Prinz, who was a refugee from Germany. He was taught by Einstein, I believe, as a student. He came to Manchester, became friendly with Turing, and they discussed computer chess and some of the early ideas about computer chess, which I guess is part of the origins of artificial intelligence. They were talking about this back in Manchester in the early 50s. Now, here's something that almost nobody knows about in regard to Turing. In Manchester, he became interested in how nature was computing. Now, I guess in the IT industry now, this is a kind of a hot topic. People, and in computer science it definitely is. People are looking for looking for nature to teach us something about computing that we don't know already. And the Turing machine is great. It's given us our laptop, and we do lots of things with it, but we want to go further. Of course, human beings always want to take things to a new level, and we're never convinced that the limitations we see are set in stone. We want to go further. And so we look at nature, we see things happening that seem to be very clever, something beyond what we're doing. And this is what Turing did. He looked at patterns in nature, shells, sunflowers, and he said, what's the plan behind this? What's the program? And he came up with some mathematics which actually gave us a proposal for how this kind of what we call now emergence worked. There's a volume of the collected works on morphogenesis. There's actually only one paper he got published on this, and he died soon after that. There's a lot of impact of the idea of emergence. You see something there, kind of more artistic materialisation of an emergence, some rules that produce strange emergent patterns. What he did was kind of rather basic. He was interested in patterns on cows' backs, for instance. You wouldn't think, probably, you go out into a field of cows, you wouldn't think, well, there's mathematics at work here. Well, he did. He came up with the idea of there being chemical reactions at work in the cow's hide, which gave rise to these patterns. And what he did, he isolated the properties of these chemical reactions, wrote down mathematical equations, got solutions. They were differential equations, essentially. He came up with solutions of these, and then, okay, this is not actually a photograph of a cow's back. This is a computer simulation. So what he had was these early computers in Manchester, and when people weren't looking, he used them to do his mathematics. And so he simulated what his equations said was happening, and he came up with patterns that actually look remarkably similar to those that you do see on a cow's back. And of course nowadays people are still this is modelling, so there's no theorem that proves that it's right, but people are still doing experiments and looking at the theory and validating the sort of proposal that he made. And this paper is one of the most cited papers in science. It's and certainly his most cited paper. And people working with Turing machines or working with artificial intelligence often don't know about this work, which the biologists certainly do know a lot about. Now, I say that those patterns are what we call emergent phenomena. And emergence in nature is very familiar to us. As we look at clouds in the sky, and we know the details of what's happening within the cloud, but the actual formations that we see are kind of mysterious, and they're subject to some kind of higher computation that we'd like to capture. And this sort of thing's going on in all sorts of contexts. Now here's a famous mathematical object, the Mandelbrot set. And as people may know, you can get the Mandelbrot set through very simple rules, but then you can, using a computer, you can go as deeply into this and deeper and deeper and deeper and find more and more strange patterns. And it's a very exciting object which you can actually see on your computer screen. If you go back to his Colossus, if you go back to early manifestations of computers, or any computer, you have this unsolvable problem that Turing isolated, which was the problem of telling basically it's the problem of telling whether your program works or not. And program verification, as you well know, is a kind of complicated problem, which is important to us. In a sense, it's unsolvable. You can't get a computer program to verify programs. You've got to do some work on it and think about it. So same sort of world. You've got an emergent, unsolvable problem. You've got models of brain activity. You know a lot about the brain now. You've got neural nets and connectionist models of the brain. At the same time, you know that what happens in the brain is very strange at times. You have, there's Einstein thinking creative thoughts which are very hard to connect to the basic brain structure. Well, more what we call more emergence, and what we say is that the mental processes supervene on the brain activity. They follow it in some sense. You get the same thing in the universe. You get a lot of physics that you understand very well. You see higher order things, some kind of higher computation which you don't understand very well, but you certainly want to get something out of that for say modern day computing even. So you've got simple rules, complex outcomes, emergent forms, and they're at the edge of what we can compute, and they take us hopefully to another level of computation eventually. Now, just have I run out of time yet? I'm okay. I'm going to sort of finish off with something about intelligent machines, and then a little bit about Turing's life to finish off with. Intelligent machines. Turing was interested in this all through his life, and he was. I guess this is what people who have problems actually living in the real world themselves would like to do. They'd like to find some kind of rules for solving problems we encounter in everyday life. Of course, all of us have problems in everyday life. We would like things to be a little bit more algorithmic. And he had this idea that he could actually build a machine which was intelligent. And this is what a lot of people nowadays would be focusing on. They don't have quite the ambition that Turing had. Turing said, I am building a brain. And of course we now know that things are a bit more complicated than that, but still we persist and we still have ambition. Now, computer science has, and the computing industry has developed tremendously since the time of Turing. When Turing died in 1954, computers were like filled massive rooms and did less than your iPhone does nowadays. But if you go back to 1997, you had probably the world's greatest ever computer chess champion, Garry Kasparov, charismatic figure, very human, very creative, and we did things with his brain which you wouldn't really think of a Turing machine doing. There was a lot of what we'd identify as human intuition, strategic thinking going on, which we might think was beyond what a computer would do. Well, IBM had different ideas. They built a machine called Deep Blue. They did enlist a lot of as many people here will know, of course, that they did enlist a lot of grandmasters to help them program the machine. But once it was programmed, there it was. It was a Turing machine. And it did battle with Garry Kasparov back in 1997. The world of chess was watching this, and it was a celebrated event. It was more than the world of chess. It was a lot of people around the world were watching this with keen interest. And Garry Kasparov did quite well to start with. He held Deep Blue at bay. And then it was like a phase transition, right? Deep Blue had learned something, and of course learning machines is important to us now. It was like Deep Blue had learned how to beat Garry Kasparov, and when the defeat came, it was dramatic, and a lot of people were shocked at that time. Of course, IBM took their machine away pretty quickly. They knew it was good for their company, to have done this, and they wanted to maintain a glow of victory over Garry. Of course, Garry thought a lot about this, and he's talked about this, and I think he's coming to Manchester next year to talk about human intelligence and playing chess and so on. But some people belittled this, didn't they? They said, well, this is number crunching, and you had a lot of grandmasters helping you out and so on. And Garry Kasparov was talking about conspiracies at times. And anyway, more human thinking. maybe computers can't do that. Well, of course, the latest media event has been another IBM victory over the human thinking. The game Jeopardy, I don't know how many people are familiar with this. I'm not very familiar, but I do know that in essence it draws on kind of quite tricky thinking, human knowledge in a broad sense, and kinds of ingenious kind of connections between question and answer. It's something where you would think that maybe the human being was going to win out. Again, IBM built a machine, Watson wins, and their experts are touring the world talking about how they did it. But, okay, there are different approaches. I'm talking to people here who probably know more than me about artificial intelligence, but there are different approaches, aren't there, to artificial intelligence, and you can live in the real world and try and build machines that do it and get them to learn and proceed experimentally. Well, Marvin Minsky doesn't do that. He believes that there's some logic that we need to master. He believes that there's some kind of deep theory that is really important to us to take it to the next level. And he takes a dim view of all these robots and so on, and he says that he makes this comment which shocked a lot of people at the time, which says that AI has been brain dead since the 1970s. And of course, people listen to Marvin Minsky. He's one of the seminal figures in the area. Now, Rodney Brooks, on the other hand, he kind of says, well, I think Marvin was talking about me when he said this approach was a kind of brain-dead one. And he does build robots, and he is experimental. But at the same time, he recognises that AI has a long way to go. And he talks about these kind of mathematical models and so on that people have built, and lots of claims are made for them, but he still sees a project which is still in progress. Now, Turing recognised that there was something different about human intelligence, and he says his idea was that if you want an intelligent machine, the benchmark is how human beings think, and there's no algorithmic test of intelligence. We know nowadays that IQ tests and so on don't really measure intelligence. They measure aspects of intelligence. So the famous Turing test is based on a human judgment of whether a machine has managed to pass itself off as a human being, and this is still, I think, important in the industry. A lot of people would like it to be a more precise test, and there are people who make proposals, but the Turing test is still, I think, an important one to us. Now, if we're talking about knowledge of Turing in the wider world, it's the Turing test that's kind of really entered the popular culture, I think. And there's a kind of it's a test for a machine being like a human. Well, of course, the joke is that sometimes it's hard for a human to be like a human. Sometimes people are not noticeably intelligent, and people go around with T-shirts that say things like, I failed the Turing test. And you see students wearing these. And there's a cartoon, there's a cartoon here, a Dilbert famous cartoon, and here you've got, here you've got the boss, essentially having problems passing the Turing test for intelligence. Right, okay, so lots of questions which, rather ambitious questions. Can a machine be conscious? Well, if a machine's going to be like a human brain, it should have consciousness. This seems to be a real foundational problem. Is the brain computing differently from a universal Turing machine? Well, that's important to us. If the answer is yes, then we're going to get a machine's doing something that our laptop doesn't. If so, how? Well, theoretical and experimental question. Can we really build brain-like computers? Turing's old question. Computer ethics, computer practicality. Do we want to? Human brains make mistakes. Human brains are quixotic. They're eccentric. It's hard to control them. You know, if you're working in a workplace, you've got people thinking thoughts that you wish they didn't. You know, that they're working, they think it's intelligent. You wish that they would follow the rules a bit better. So maybe machines with rules are kind of more what we want. And